So we haven't finished the problem of the polymer that we started last week. I'll quickly remind you where are we standing and what exactly we are trying to solve and why we're solving this. So polymer, ball, we have something that this, have a pulley, have a weight, pulling on this with strength tau. This is our elongation, Lx, and eventually we described everything, the energy, as a sum over all the different monomers. So each of those guys, this is a monomer. We summed up over the effective energies of the monomers. Why effective? Because the regular energies, which were either zero energy if the monomer is elongated along the x-axis, or epsilon if it's oriented along the y-axis, but it wasn't enough in order to describe the energy as an additive quantity of all the energies of different particles. So we had to modify the definition of the energy per monomer, and this is our effective energy. So the effective energy could be what it could be, either a tau or epsilon or minus epsilon, right? This is not me. And what else? No. So either a tau or minus a tau, or epsilon or epsilon. So each of those values of the energies were related to each energy. So this is for the energy that's oriented to the right. This is for the energy that's oriented to the left. Yes, or the other way around? I don't remember.
סטאס, לגבי הסטודנטית שבמעורבות...
אני אבוא?
אבל כאילו שישגיחו עליה ממדור בחינות?
עניין כספי או לא?
טוב.
It's related to your quiz tomorrow. Some administrative stuff. Do you remember how we describe these energies? I think it was a tau minus a tau.
סטאס, סליחה. אם מגיע לך בוחנים, אני לא נשלם על זה. אז לקחת?
זה נראה לי כאב ראש. הם יבואו?
היא אומרת שמגיע לך.
מגיע להם, לא לי.
כן.
אני לא יודע, 8.5, אבל איך נחלק אותם פה בכיתות?
איזה כיתות? זה פה ב-221?
כן, וצריך עוד להגיד להם את זה.
היא תשלח לפה ולשם.
טוב, בסדר.
ולמורות.
שזה לא יצא בלגן רק בבוקר.
טוב, אז מתי אתה כאן?
עוד 45 דקות. את תהיי פה ב2:45? רוצה לדבר על זה ב2:45?
2:45, כן, אני פה.
Sorry.
It was opposite, right?
It was the opposite, right. It was the opposite. So, we have, for any monomer that's oriented to the right, we had the energy of minus a tau. For the monomer that was oriented to the left, it was a tau. For any monomer that was oriented up, the energy was epsilon. For any monomer that was oriented downwards, the energy was again epsilon. So those are the different energies, effective energies, per each monomer. So the moment we have written our total energy in this fashion, okay, we have, and all the energies, effective energies of the different monomers are oriented in a way that is not connected to the orientation of any other monomer. So basically, they are not correlated, and all the different monomers are independent, at least when we write their energies in this fashion as an effective energy. We can say that the partition function, Z, it is a multiplication from I goes from 1 to n of all the partition functions of different monomers, right? So two conditions, additivity of the energy, right? And factorization or independence of all the different particles, okay? So the moment, so the independence of the additivity of the energy is written due to the fact that we write it down as an effective energies, and the independence comes from the definition of the problem. Okay, so we have this multiplication for the partition function in terms of the partition functions of single monomers. All the different ZIs, okay, we can write down in the following fashion. Is just we sum up over all the possible states of each monomer. So each monomer can have 4 states. So it is the orientation to the right, the orientation to the left, the orientation that is upwards, and the orientation that is downwards. Okay. For each orientation, which is our state, we write down the energy that is related to this state. Okay, so the state when the particle, the monomer, is oriented to the right is minus beta, and we have this minus a tau. Plus, for the orientation to the left, we have an exponent of minus beta, and here we have the energy which is minus a tau. So, no, here it's minus, I'm sorry. Here it's minus a tau, and here it's a tau. Orientation to the upwards is e to the power minus beta epsilon, and orientation downwards is e to the minus beta epsilon. Okay. So you see all the different ZIs are independent of the index I. So I can tell you that ZI equals to Z1, which is e to the power beta a tau plus e to the power minus beta a tau plus e to the power minus beta epsilon plus or multiplied by 2. So this is our Z's. Great. So remember, the moment that we have the partition function, which is now, it is simply Z1 to the power n, because all the ZIs are exactly the same, they're similar. We can compute whatever you like. Specifically, we can have that the free energy is minus 1 over beta log of Z. And using this thermodynamic quantity, we can compute all the other thermodynamic quantities. The question was, okay, first of all, to compute Lx average. Okay? So how we are going to perform this? We of course can relate Lx to F by some derivative. If you remember, we can write down the free energy, and the free energy is going to behave somehow, so it's related to the energy of the system, etc., etc. Okay, so we usually have that in U there is tau dL, and this is how we can define or find the dependence of L on U. Using the Legendre transformation, we can find the dependence of L over F. Okay, and this is how we can solve it. But this is the nasty way, the unpleasant way of thermodynamics. You have to remember all the different connections, all the different relations between how you define energy and then how you define free energy. And there is a bunch of derivatives that you have to use all the time, and you never know what kind of derivatives you have to use now, because there are a bunch of them. Okay? Maxwell relations, and etc., etc., etc. It's all very confusing. But in statistical mechanics, nothing is really confusing. Why? Because we can always use the basic definitions of probability. We look on this guy, okay, Lx average. Okay. So instead of going backwards to thermodynamics and all those definitions, the energy, free energy, Legendre transformations, we say the following thing. What is Lx? Lx, we can basically go over all the different Li dot x. So we are going on the different orientations of each single monomer, and we compute its orientation along the x-axis. I goes from 1 to n. Okay? So I write it down as a sum of I, Li, x. Okay? So this is the average. I have done nothing wrong. I just written, all right. I have just written the definition of what is the elongation of the monomer, and the elongation I just need to sum up all the different orientations of the monomer along the x-axis. I don't care if it's pointing upwards, because then the contribution is 0. Some of them are going to point to the left or to the right, and some of them to the left, and I just need to sum all of them and then take this average. Now this is nice and easy. Why it's nice and easy? Because you all sometime in the past had probability 101. And in probability 101, you all know that the average of the sum is the sum of the averages. So you can write this down as a sum over I from 1 to n of Lix. So I just need to compute those Lix. And now the fun part comes. The moment that we have written the partition function in this factorized way, each and single particle behaves independently, and I can compute the averages of any observable by using the laws of statistical physics or statistical mechanics. I'm looking on each single monomer as it is independent of any other monomers, and I compute the different observables by using the probabilities of being in each state. Right? I don't need thermodynamics, I don't need this part, I don't need Legendre transformations. I only need to know the probabilities of each state of my system. Now, my system right now is a single monomer, and it has 4 different states. I know the probabilities of the different states, so I can compute all the different observables. Okay. So basically, I can look on Lix, right, and I can say the following average, and I can write it down in following sense. So the probability f of being oriented to the right multiplied by what is the elongation of the monomer when it's oriented to the right, it's A, plus the probability of a single monomer to be oriented to the left multiplied by what? By the size of the monomer, orientation of the monomer, it's minus A, plus the probability of the monomer to be oriented upwards, but when it's oriented upwards, okay, it's 0, right? So the only thing that we need is the elongation along the x-axis. Okay? So it's 0. The same goes when it's oriented downwards. Do you see what I've done? Instead of going and compute some averages by using cumbersome mathematical connections of thermodynamics, I'm separated all the system to many small systems, which are all identical. And I know the different states of each of those microscopical systems. I know the different states. I also know the probabilities of those states. Okay? Because what is f when it's pointed to the right? I only care about the energy of the state. So this is e to the power minus beta, and the orientation to the right is minus a tau divided by z1 multiplied by a. Plus, this probability is the exponent to the power minus beta multiplied by the probability when it's oriented to the left, which is a tau, divided by z1 multiplied by minus a. That's it. This is the this is not f. This is Lix. That's all what I need. Right? That's all what I need. Now, see, this Lix is again, because all the monomers are identical, is independent of I. So I can say that Lix average equals to L1x average. I can take only the first monomer and care only about this one and say which is A. In here I will have e to the power beta a tau plus e to the power minus beta a tau divided by z1, and z1 I know what it is. It is this guy over here. So it is e to the power beta a tau plus e to the power minus beta a tau plus 2 e to the power minus beta epsilon.
Stas, it
Yes.
should be minus in the numerator.
Where now? Here for minus 8. Thanks. Now this is only L1. We can then go to this definition and we see that all the Li's are exactly the same. So Lx average, which is a sum I goes from 1 to n for Lix average, equals to, because all of them are identical, I just take this formula over here and multiply it by n, which is n a e to the power beta a tau minus e to the power minus beta a tau divided by e to the power beta a tau plus e to the power minus beta a tau plus 2 e to the minus beta epsilon. This is Lx average. Again, the only thing that I cared about, the moment I written the partition, the original partition function in this form, and I have additivity of the energies, I treat each single particle independently as if it was a macroscopic system. I know all the different states of the system, I know the energies of the system, I can forget about all the different relations of F to L, and etc. etc. Microscopical statistical physics comes really, really fast, and I can use my intuition and my probability knowledge. Okay? I don't need to remember or memorize different functions. Okay? So it's all based on probability, and it's all based that there is a specific form of how those probabilities looks like. They provided by what is called the Boltzmann factor over here. Okay, so, but what was the question? The question was not really about the elongation. The question was how the elastic modulus looks like, or 1 over the elastic modulus looks like. So we basically say the following thing. If we have tau, which is our external force, the elongation that we are applying to the monomer, you can think about it as if it's an elastic material, okay? And I can compute the different elastic properties of this material. So basically tau, it is some kappa multiplied by L. Now, of course, everything is fluctuating. Some monomers are now in this position. After a while, they're going to be in that position, and then the orientation, and then they can sweep again to this orientation. So the only thing that I can say that I'm looking on the average Lx. Okay. So from this relation over here, tau is a parameter that I can control, okay, in a lab. Lx, this is something that I can measure. And from this property, or from this relation, I can come and describe how this kappa, or usually it is, it's going as 1 over kappa, because I'm going to look on Lx equals to 1 over tau multiplied by 1 over kappa. How this 1 over kappa looks like. Okay. And I can make a prediction, and I can go to the lab, and I can measure it, and I can explain how all this is related, the elastic properties of this monomer, a slurry polymer, that for example can be a DNA, and I can describe to you what are the different elastic properties of the DNA. Very long molecule, at least using this very simplified picture when all the different monomers are somehow unrelated to each other. All right, so let's do it. Now, the trick is, in the lab, we never apply extremely large force, because if I apply a very harsh force, it will tear down the system. So everywhere, when I'm trying to perturb the system a little bit, so this tau is some sort of a perturbation. The system can be free, right? And I apply some force. Usually the force is small enough, and we are working in the regime when the elongation, okay, is proportional to the force. So this is called linear response. So usually all the elastic properties are describing linear response when I'm assuming that all my forces and all my perturbations are small enough. Okay, in a second we will see small enough compared to what? Yes?
If we want to study phase transitions, it's the opposite, right? We want to exert a lot of force in order to watch the...
So you want to tear down the system usually, yes. Yes. So phase transitions occur when I do something abrupt and the system, or I push the system far enough somewhere where it's behaving completely different from what I'm expecting. So linear response is, well, I have a equilibrium state, free space, and I'm flying slightly on the system and I want to see how it's responding. So it's very different from phasor relations. Yes. Okay. So what do we do? So we can say the following thing: 1 over kappa. It is d Lx average to d tau. So in order to compute this 1 over kappa, we need to perform a derivative of this guy. Now, it looks kind of nasty because we have a lot of exponentials over here, but I want to work in this regime of linear response. So before, and it's usually a good practice, when you have a complicated function, and you need to perform something, some operation on this function, like take a derivative of it, it's usually to first understand in what regime you're working, make some sort of a massage to this function, okay, work a little bit or transform this function such that this regime is applicable, and only then take all the different derivatives. It's easier. Why I'm saying to you, so when you're sitting behind your desk, not in the classroom, in your home, well, it's not really hard to take any derivative, right? In the worst case scenario, you're going to use Wolfram. But when you're during the exam and you have limited time and you need to perform a derivative, usually the best practice is to make some sort of approximation, which depends on your regime, and only then perform the derivative. Okay? I'm talking from experience of reading huge notes of derivatives without any end to end. Yes, questions. There was a question. Yes. Okay, yep. I don't need to take the derivative. The question is, why do I need to take the derivative? If it's indeed linear, okay, you don't need to take the derivative. Okay, so this is the answer in some sense. When I Taylor expand this guy around 0 for tau, I'm going to obtain something multiplied by tau, and I don't need to take the derivative. Yeah, you're right. But this is the definition. Okay, so our tau is small. What's happening in small tau? So let's look on the different factors that we have inside. Na, we can keep it as it is. We really don't care about the Na. So we are looking on e to the power beta a tau, which is e to the power a tau divided by k Boltzmann t. Now I'm assuming that tau is very small. Tau is very small with respect to what? We're assuming that a tau divided by k Boltzmann t is small. Okay. This is the approximation. This is the limit where we're working. Okay. Of course, when the temperature is going to be extremely small, this is not applicable. Okay. But we assume that everywhere where we are working, this relation holds. Okay. Now, so in this limit, what happens? So we can approximate e to the power beta a tau. We approximate it is as 1 plus beta a tau. Okay. Now, e to the power minus beta a tau, we approximate as 1 minus beta a tau. Okay. The same goes from the terms that appear in the denominator, this guy, and this is not, well, it's still there. Okay, so what we have, Lx equals to Na, x average, and what we have inside. So instead of this guy, we have 1 plus beta a tau minus 1 minus beta a tau. divided by 1 plus beta A tau plus, right, 1 minus beta A tau plus 2 e to the power minus beta epsilon. So what do we have? Lx average equals to NA. 1 and 1 disappears, and over here we have A tau beta multiplied by 2.
But you divide by 2.
Sorry?
You divide by 2.
Where I divided by 2?
In the במחנה. לא, במחנה.
Over here?
כן, כן.
In a second. I'm going to come over there. So here I have 2, and I here still have 2, so plus 2 e to the power minus beta epsilon. Okay. So what do we see? We see that Lx average equals to, or approximately, goes as n a squared beta, or let's use it tau. Here we have K Boltzmann T 1 plus e to the power minus beta epsilon. So if you're looking on our prediction, what we have is Lx, not Lx, or 1 over kappa, equals to NA squared divided by K Boltzmann T, 1 plus e to the power minus beta epsilon. Or, let's write it down, K Boltzmann T. Okay, so that's basically it. This is the behavior of 1 over kappa. And what can I say? This behavior describes the response of the system to temperature or to external force. It have a very specific dependence on T. Therefore, so we're basically done. Now we can go to the lab. We can estimate this guy. Okay, we can estimate this guy, describe how it behaves exactly. Now there is a nice thing about this. So if you look on large enough temperatures, so for small temperatures, this doesn't really work because, well, depends on what is the temperature. But we see that for very small temperatures, this is not going to be applicable. We can look on the limit of large temperatures. Okay. So in the limit of small temperatures, this is probably not relevant so much. But in the limit of large temperatures, okay, we see that the prefactor is going as 1 over T. So in the limit of large temperatures, we have a decay. It's going to be modified in the limit of small temperatures because all those expansions do not contribute, or they simply not correct, and we indeed have to take this derivative and check what's going on. But in the limit of large temperatures, there is a decay of the compressibility, or I'm sorry, the elastic modulus with temperature. Now, this is something that we don't really anticipate for spring. Because what happens to a spring? A linear spring, if you go to the lab and you heat it up a little bit and you try to measure the elastic modulus, you're going to see that it's going to increase. Right? So as you heat the temperature, it's easier to make an extensions to your system. Why? Because the molecules, which are constituents of the spring, they're more and more loosely related to each other. So it's easier to pull the spring apart. So this is the elastic property of any regular spring. You heat it up, and it's easier to extend it. For this polymer, at least for large temperatures, in the limit of large temperatures, we're getting the opposite effect. So what is actually happening? You heat up the system beyond a specific temperature. You heat up the system, okay, and what's happening to the system? It's actually harder to pull it apart. You heat it a little bit more, and it becomes even more harder. Okay? So it's the other way from our naive expectation. Why it's happening? You increase the temperature. So what happens is that the system is actually spreading. As you increase the temperature, the system is spreading in your y-axis much more than it's spreading in your x-axis. And it becomes harder and harder to pull it apart because it has much more options to actually go up in the energies or make those orientations that are upwards. That's actually what contributes to this decrease. Now, we couldn't say that in the first place. You can say, yeah, you actually allow this degree of freedom in the y-axis, so this is why you're at the end are going to get a worse elastic modulus. But it actually comes from the math. Okay? It's hard to expect this result, okay? And it appears from the mathematical expressions. And it depends on the fact that we allow the system to express itself in the y-axis, but it's not so trivial. Okay? The only thing to remember is you allow the degree of freedom in y direction, and all what you thought is true about one-dimensional system like a spring is already not true, at least for large enough temperatures.
Is it true for real polymers?
Sorry?
Is it true for real polymers?
Yeah.
Yeah?
Yeah. For real polymers, it's even more true because what they start to do as you increase the temperature, they start to make knots. And the moment that it's knotted, actually, not just unrelated monomers, but the moment it's knotted, it's even harder to pull it apart. Okay? So it's a poor approximation for real polymer, but it's still qualitatively true. And for real polymer, because all the monomers are somehow correlated to each other, the effect is even stronger. All right, so we have something like 5-10 minutes left. And what I wanted to do today is actually much more. But let's start and do another example. All right. So we had this example of a polymer. I would like to solve another example, which is Einstein model for solids. Okay. So what we're going to 1907, I think. Yes. So it's around 1907. So it's after his magical year. So it's related to experiments, and in experiments, okay, I can have a system, I can have a solid, okay? It can be a bulk of metal, it can be a bulk of some other material, and I can heat it up, and by heating it up or cooling it down, I can measure the specific heat of the system as a function of temperature. So CV as a function of temperature. And what I see that happens in experiments is that it goes down towards zero as the temperature goes to zero. It rises up, and then it approached a constant, and it seems that this constant is independent of the material. Okay. So I'm heating different materials, and the specific heat approaches a constant which is independent of the material. Okay. Another thing is how it decays towards zero. So it's always two asymptotic limits in physics. We usually work in some asymptotic regime. So this is the asymptotic of large temperatures. So T is going to infinity, and here T is going to zero. We know it's approaching a constant, which is usually independent of the type of the material, this constant. And we know that when t goes to 0, it goes to 0 as t to some power, t to the third. Right? And those two limits are universal for any or almost any regular solid. Okay, so the majority of the solids, this is what you see for the specific heat. You see something that approaches to a constant, and you can say exactly what this constant is, and you see that it when in the regime of low temperatures, there is a t to the third. Universal laws, so it's basically almost independent of what type of solid you're going to use. Physicists love general rules, love general equations, right? Something that it applies everywhere. Okay, so our belief that Newton's laws apply everywhere in the universe. Okay, well, maybe not exactly applicable, right? When you're going to the limit of very, very large masses or very high velocities, but in the other regime, it's always applicable, no matter where you are. So when you see a universal behavior, you say, well, there is something to it. There are some universal laws, some very interesting physics, or at least universal physics. Interesting, universal, it's almost the same for physicists. Okay, so this guy, you all know him, tried to explain this phenomena, and I think this was the first attempt to describe it. It's several years after Planck, so you already have this theory of black body radiation and photoelectric effect. So Einstein thought to use very similar ideas, which are already been published in his paper on photoelectric effect, to describe what is going on for the solid. Okay. So Einstein picture, it's actually very simple. It says the following thing. So what is a solid? So it's a bunch of atoms. Now, for them it's already a pretty strong statement, because the final proof that there are atoms arrived in 1908, I think, by Jean-Baptiste Curie. So we have a bunch of atoms, and all those atoms somehow vibrating. They are vibrating and they're doing something, right? Now each atom can vibrate in the x direction, in the y direction, and let's assume also in the z direction, so it's pointing towards you. Now, Einstein assumes that each atom is a harmonic oscillator, simple harmonic oscillator, and it vibrates. Okay. Now, we now already know that the vibrations, okay, of a harmonic oscillator, if we use quantum mechanical description, so for each degree of motion, it can be degree of motion in the z direction, in the y direction, in the x direction. Okay, they are quantified. Right? And we know from quantum mechanics that it is n multiplied by h over 0 plus 1/2, right? Or sorry, n plus 1/2 multiplied by h omega. Okay. So those energies, we know them from quantum mechanics, and we know why they're such energies, because we've seen somebody solve the Schrodinger equation for a harmonic oscillator, and those are the eigenstates of the energies, and we know how to obtain it, or at least we've seen it once on a board. Now, Einstein has no idea about the Schrodinger equation, okay, not yet, but he, in his photoelectric effect, which is actually the basis of quantum mechanics, although he opposed it, okay, we know that there are quantas of energies that molecules or atoms or parts of the material can actually absorb. So Einstein makes this connection that the vibrations of the molecules, of the atoms, are coming in quantas. Okay? Now, he doesn't know about this 1/2, and you don't really need it. So for him, says this is n multiplied by h bar omega. Okay? Where this h bar omega coming from? This is the same h bar omega that appears in the black body by Planck, and it appears in the photoelectric effect. They already know something about the quantas of the energies, and they know that there is an n that stands over here, which obtains 1, 2, 0, 1, 2, 3, 4, 5, 6, 7 integer numbers. Okay. So Einstein assumption, it's always a very simple model with Einstein. It says all the different atoms have exactly the same, oscillate in the same fashion, and all the different vibration in the X, Y, and the Z, they all vibrate exactly in the same form. They can have the same energy for basically this omega over here is the same for everybody. The same for all degrees of freedom. Great. So why do he need? Why does Einstein need this assumption? Because it's the simplest thing that you can imagine, right? First you say, well, all the particles, all degrees of freedom are exactly the same. They all can have different energies. Why they can have different energies? Because of this n number over here. So the differences on the energies of different atoms coming from having different quantum numbers without the word quantum. Right? Now, but in order to solve it in statistical mechanics, what do you need? You need independence. And the another thing is additivity of energy. So additivity comes because they are independent. This is why everything is additive. All of them also are identical, which is another simplification. So the two conditions that we mentioned before about solving any system, complex system behavior in statistical physics, additivity of energies and independence, actually are assumed by Einstein in his model. Why he assumes it? Because this is what he can solve and this is easy. At least easy for us now, probably much more complicated hundreds of years ago. So what do we know? If this is the description of each single particle, and all the particles are independent, we can say that the partition function of this system is just the multiplication of all the different degrees of freedom. And how many degrees of freedom do we have? If we have n particles, and we have three-dimensional motion for each particle, so this is 3n degrees of freedom. So I goes from 1 to 3n, and here I'm going to have zi. Moreover, all the zi's, zi is independent of I. So I'm going to say that this is z1 to the power of 3n. Okay. The next thing that I need to do is to compute this z1. What is z1? z1 is a sum over all case j goes from z, or n, I'm sorry, n goes from 0 to infinity, e to the power minus beta en. This is the definition of partition function. So what do we have inside? We have a sum n goes from 0 to infinity, e to the power minus beta, and the en is n h bar omega. N h bar omega. Okay. Now look on this guy. This is a sum n goes from 0 to infinity of e to the power minus beta h bar omega to the power n. Geometry. This is a geometric series, and it is a sum of a geometric series. Okay. So this sum is 1 because for n equals 0, the term here is simply 1, divided by 1 minus e to the power minus beta h bar omega. So the partition function is simply 1 over 1 minus e to the power minus beta h bar omega to the power 3n. We can go and describe what is F. The free energy is minus 1 over beta log of z, which is 3 n divided by beta log of 1 minus e to the power minus beta h bar omega. So this is the free energy. The moment that we have free energies, we don't have free time, we can describe the specific heat, and we'll do this next Sunday, and we will see if the Einstein ideas are actually correct, or maybe this time Einstein was wrong. Okay, so let's wait till Sunday. That's it. Okay, so the quiz, I'm going to publish what are, when I solve the bureaucratic problems, what classrooms, but there are going to be two classes. One is going to be over here, the other one is going to be in the other class. Okay, so the other class is 221 in, so room 221, classroom, or building 203. And I'm going to publish who is going to sit where the moment I solve this with the secretaries. It's 1 hour. It starts at 8:30. This is the final time. And good luck, all of you.
So the material is only on the first part, the thermodynamics.
Everything that is related only to the thermodynamics.
Okay.
Up to phase transition, including phase transitions.
Okay.
So everything except for polymers and
Everything before we started statistical mechanics. Okay.
And